Hi, everybody. I'm Julian. You might not recognize me because I'm not wearing tweed today because it's been far too warm here, but you can normally find me wearing tweed. I'm a Ruby developer from Bath in England. So this is the beautiful city of Bath. Just so you know, it's not London. So I do not live in London. I live in Bath. And it's called Bath because we have many baths, and we do sometimes have showers as well. So I work at a small open source company called Red Hat on a project called ManageIQ. And you can find us on GitHub/ManageIQ. We're always looking for contributors, and we're always hiring. So if you want to come work at ManageIQ and Red Hat and write open source, come speak to me afterwards, and we can see what we can do. So thank you to everyone that came to Ruby karaoke last night. I woke up this morning after getting in very late, and I was so tired, and I was just lying there with my alarm, just going 5 more minutes, which I think this is what the lazy yoke is also saying. I hope so, anyway. So the name of this talk is It's More Fun to Compute. That comes from a track from this album called Computerwelt by a German band called Kraftwerk, which this album and this band make lots and lots of electronic music using synthesizers. So today we're going to talk about synths, but not these kind of synths from Fallout 4, these kind of synthesizers, electronic instruments. So I have here with me a few of my instruments from home. I have my Arteria Mini Brute. I have my Korg Volca Keys, which is a polyphonic synth. I have my Korg Volca Beats, which is an analog drum machine. And then I have my Little Bits, who teamed up with Korg to make the Korg's Little Bits synth. So the first thing you need to know when you want to learn about synthesizers is that they're basically created using oscillators. And oscillators are a small piece of electronics that just generate a pattern, and they just go around generating an electrical pattern. And those patterns are called waves. So there are a variety of different waves that synthesizers generate. So we all might be familiar with the square wave, sort of on and off, very kind of up and down. We use this a lot in computing to turn things on and off, and that's pretty much the one we're used to. You may also know of the sine wave, which is a bit more kind of fluid, but we don't tend to use this one in everyday computing because we can't have multiple values. We can only have zeros or one. Another wave that you might not be aware of is the triangle wave, so called because they look like triangles. We then also have the Sawtooth Wave, which, if I'm right, it could be the Nokogiri wave. Is that correct? Because I think that means saw. And the cool thing with saw waves is that they can also go in reverse. So they can sound really different just from the direction that they're going in. And, of course, our dearly beloved Google Wave. May you rest in peace. And then the last wave that you need to know about is noise, which that basically all it is it's just noise. It's messy, but it can also be beautiful. So let's have a quick demo to see what those actually sound like. So if because I plugged the wrong thing in to the wrong place. Right. So to kind of show you what the waves look like, I have a demo written in processing. I didn't write this, somebody else wrote this. It's a visualizer that shows sound. As you can see, it's currently the sound of my voice. Hopefully, it should show the sound from my synthesizer. So if I load up my camera, let's make this a bit smaller. OK, so So this is my synthesizer here, and I can actually generate different wave shapes using the oscillator. So this is what a sawtooth would sound like. Which doesn't seem to want to work to show you the visuals. Let's try that again. So this is using Ruby to kind of, and what's called a Fourier transformation to show you the audio. And it's kind of sorry, it's not quite exactly there. And so then this is a square wave. Obviously, it's not very square on there. If I could take some more samples, we could make it work a bit better. But as you can hear, they're very different in sound. This one kind of gradually goes up and then stops, and this one is very kind of on and off, on and off. This is the triangle wave. It's very quieter, a lot more subtle. And then this one is, for any of you who didn't have analog television, this is what happens when you tune to the wrong television channel. Or when you're trying to go between radio channels. This is noise. This is like the sound of the Big Bang. It's basically all of the other sounds combined. It's a very good sound. I like it. So the next thing that you need to then know with synthesizers is those sounds were very plain and boring by themselves. So we need to learn about envelopes. And so we have the type of envelope here, which is attack. Oh, that's cool. Ruby processing. You have different types of envelopes. You have attack, decay, sustain, and release. Now, you may think that that's kind of some killer kind of combo move in some sort of fighting game. But what a envelope is it changes the structure of the sound. So if you start from the beginning, when you press the key, the attack is the amount of time it takes the sound to go from 0 up to the maximum sound level that that note is going to make. And so you can increase or decrease the amount of time of that. The decay section is the amount of time it takes to go from the maximum the sound will be down to the level set by sustain. And on here, sustain isn't a length of time, it's the volume. So that's the volume of the note. And then once you've taken your finger off the key, everything after that is the release. And so you can have longer notes or you can have shorter notes. So let's have a look at that. So again, we use the sawtooth. And when I take my finger off, the note stops. If I increase the attack and decay, you can see it takes a lot longer for the noise to come once I've pressed the button. Or if I move the camera, you could see. Whoop. Let's remove them again. And then if we increase the release, when I let go, the sound will just keep carrying on. And the cool thing is that's why then we can use noise. You can make it, instead of sounding really harsh and like static, you can kind of almost make it sound like a cymbal. Which is why these are called digital synthesizers, analog synthesizers, because they synthesize sounds. So just by changing the different waveforms and the different envelopes associated with each waveform, we can replicate more or less every kind of instrument, which was super exciting to composers in the 60s when these things came about, because instead of having to hire a whole orchestra, you could just turn up with something like this, although back in the 60s it probably would have been the size of this stage. You could just turn up with that, twiddle a few knobs, and make a whole orchestra's worth of music. So you might be thinking, wow, this is super cool. These instruments look great, but what has this got to do with Ruby? And Not everyone can go out and buy or even carry around analog synthesizers. They're quite large, and you've got to maintain them just like every other instrument that you would have in your home. So the great thing is we can now have digital synthesizers, and Psych Pie is an example of that. It's a Ruby application that runs on top of something called Overtone, which is a digital synthesizer. So this is Psych Pie, or as I prefer it, Sonic Pie. And the problem I had with Psych Pie is when I would first see code like this, I was like, wow, I don't know what a saw is. Do I want to use it? I don't know. And what's this play 60 and attack and decay and sustain and release? But now, having kind of studied a bit more and then bought some actual instruments where I can physically move all the buttons and see how it changes the sound, this kind of code example isn't so scary anymore. It's exactly what we did with this. We had a bit of attack, a bit of decay and sustain and release, and we played the note 60, which is middle C on a piano. So that's what that code sounds like, but on an instrument. But let's have a look at that in Psych Pie. So if I borrow this. So this is Psych Pie, and you just type in Ruby, and then you can run it. Oh, no, we can't. Psych Pie, right. So Psych Pie was created in the UK by a gentleman called Sam Aaron. It's called Pie because it was made for kids mainly to teach them programming, and it can also run on the Raspberry Pi. So there's this note again, this play 60, which stands for middle C. As you can see, they're pretty similar. And if we change this one and then go to this, which is the code example we had on the slide with a bit of attack, a bit of decay, a longer sustain, and then a release, you'll see it will sound different. So that's that same note, but it's actually lasting longer now, which is what we did with the buttons over here. Pretty close, right? And so with these few patterns, you can go on and create amazing pieces of music, which we will see afterwards. So you're now thinking, this is really, really cool. We can now write music with Ruby and Psych Pie, and then I can come over here and I can play my instruments. And you're thinking, that's really great, but wouldn't it be cool if the instruments could maybe talk to the computer? After all, we're programmers. And it turns out that you can do that. There's a protocol called MIDI, which was created in the 80s, I believe. But just before we start talking about MIDI, I'd like to talk about this lady, Wendy Carlos. She is an amazing composer who used synthesizers to make her music, and she made one of the first mainstream synthesized albums called Switched on Bach, which was classical music, but instead of having an orchestra made exclusively with an analog synthesizer that she played herself and cut it and edited it and made all of the songs. She then went on to create soundtracks with synthesizers on films like The Clockwork Orange and Tron. And so if you think that all of these sounds sound quite futuristic, like they do in Tron, they're actually all from like the 50s and 60s, so retrofuturism. But anyway, back to MIDI. So MIDI stands for Musical Instrument Digital Interface. And before MIDI came about, every manufacturer would have different ways of their instruments talking to each other, and they wouldn't be interoperable with any other instrument. But when MIDI came along, you could just connect all of your instruments up with this little cable here, or two cables, because they only go one way. You've got into your instrument and then back out. And you can also daisy chain them. And so MIDI is just a messaging protocol. So first of all, you say what you want to do to the note, whether you want it on or off. and then you say which channel, so you can have up to 16 instruments, and then the note number. So this is where the 60 comes from earlier, or C3 is another way of naming it. So this all comes from physical pianos. So C3 is middle C. So if we changed it to C4, that would mean it goes up an octave. C2 would mean it goes down an octave. And then the note velocity is how hard you press the note. So I don't know if I have that turned on here. No, I don't have velocity on this, but what you can do is you can change, so you can make it, the more gently you press, the softer the sound, and the more harder you press, the more sort of impact the sound has, just like you would do on a piano. So when some of you heard MIDI, you might have thought, oh, MIDI, that's that awful ringtone sound that I used to have on my mobile phone, and it would have sounded a bit like this. And you'd be like, oh, this isn't very nice music. Why would proper musicians want to be using MIDI? But this is a misnomer. MIDI is, in fact, just a messaging protocol. So it all depends on what instruments you hook up. So on your old mobile phones that would have those awful ringtones, it's because you've got a tiny phone with not very much processing power. Whereas if you had a large synthesizer like this, you could get some amazing stuff. But maybe carrying around a synthesizer and a speaker just so you could have Tetris theme tune play in full fidelity might not be very practical. OK, so let's see if we can get Ruby to talk MIDI to our instruments. Right, which demo have we got? Can you see that? Let's make that bigger. So what we're first of all going to do, we're going to connect to a MIDI device, and then we're going to play these notes. Let's move this over. And then sleep for a duration. So let's run this. Simple MIDI. So it's got all of these different devices, and you might not be able to see that. I want to use my mini brute, so I'll choose 7. And that was Ruby playing music. Unfortunately, I didn't turn any of the notes off, so if I'd not turned off my machine, it would have carried on playing indefinitely. Because this is the instruction to tell it to turn a note on. I should have also put on to turn a note off. Where's my talk? And so it's not just a simple bit of code that we can run. We can also kind of create beats, and we can use this library called Topaz to set a tempo. So if I turn this one on, so this basically just goes around a loop and plays certain notes at a certain speed. Drum beat. Select device. Is it this one? Nope. Problem is I have too many devices. Let's try that one. OK, right. Sorry. So many cables. Right, that's that one. Huh. Oh, that is working. Ah, it's not plugged in, that's why. So many cables. I apologize. So this is just a simple drum beat written in Ruby. So if we were then to change the tempo of this to, say, 240 beats per minute, and restart that, now we can have a bit of a faster drum beat, make it a bit more dance music. Or I guess maybe at the end of the night when we're getting a bit tired, we could just slow it down. Oops. Although I don't really know how you would dance to this. Excellent. So that's just a tiny, tiny bit of Ruby code, and we can already create a drum beat. What else have we got? So when I realized that I can control my instruments using Ruby, I was like, well, what other things could I do that would be fun to control? That would be fun to use music for. And I was thinking, when you're working on a project and you're running your tests in the background, you don't really look at the screen where it's like dot, 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 red, pass, fail, whatever test suite you're using. That's not particularly useful. What would be more useful is if you could have some music generated while you were running your tests. And so by the power of MiniTest, I was able to write a little MiniTestReporter that will generate a MIDI beat. Would create MIDI messages for me that we can send to our synthesizer. And so here's our simple tests. It's just as all good tests should be. We're asserting true when we're passing. We're asserting false when we want our tests to fail, as I'm sure you have all in all of your code. So let's go and run that and see how our tests would sound if they were music. Where's that? CD, musical, CD, musical reporter. So we just run rake test. Oops, no we won't. That should be a 0. You can also, instead of having to choose from a drop-down of which device you want to do, you can also pre-select it, which is what I'm trying to do here. Nope. Why do you not want to run today? Is it plugged in? Oh, I've unplugged the USB somehow. Oh dear. Sorry. Right. Now it should work. Luckily we got tests, right? Otherwise we wouldn't know if it worked. Oh no, come on. Right, try again, last time. Okay, so that did not work. Why is that? Okay, sorry about that. Let's just try one more time. And I know what you're all thinking. You could make music with this, right? With different notes, whether if it passes, it makes one note. If it fails, if it skips or if it errors, you could make music. But annoyingly, MiniTest randomizes. So it will be different tests running each time. So it should never sound the same. So can you imagine that going in your office all of the time when the tests are running? How cool would that be? And every time you heard a sad note, you'd be like, oh, the tests are broken, I'm sad. But every time you heard a happy note, you'd be really happy because everything would be green. Yay. So I'm going to push this gem up, to make this available with some configuration options so you can all have happy musical offices, hopefully soon. Right, okay. So the other thing, once I then started playing with instruments, I was like, cool. So now we can have our tests passing and failing. I wonder what sounds better. Whether, does quicksort sound better or is bubble sort better? Because we all know which one's faster, because we can run all of those tests and metrics, but that's not really important. What I want to know is how it sounds. So let's go find that demo. Right. Where did I put it? Not there. Ah, yes, it's in sequences, sorry. Right. So, let's close these. So here we have a simple bubble sort that plays a note, and then we have a simple quicksort that, again, plays the note of the item that we're sorting. So we're sorting items between 50 and 100. First of all, we're making it a random array, and then we're sorting them and seeing how it sounds. The reason I've chosen 50 to 100 is that's in the range of the instrument. So if we try, first of all, let's try quicksort. See how that sounds. It doesn't sound at all. Oh, I know why. It's because I've put it in Psych Pie, I believe, not on my synth. Where did it go? Sorry. I've misplaced. Aha, quicksort versus bubble sort. Is that it? There we go. I had this demo for Psych Pie. Let's put this in here. Let's find an empty window. Right, there we go. OK. So let's find this. Right, it's all plugged in, I believe. Nope. Right, OK. So, yes, we make the numbers between 50 and 100. So let's try quicksort first. Doesn't really sound very musical. Not very nice. I'm like, maybe I don't want to use quicksort. Maybe the computer doesn't like that. Let's try bubble sort. Well, that one sounds a little bit better, I think. So now we can also hear how our algorithms are written. So we can not only compare to see how quick they are and how efficient, but also maybe we could see how they sound, because computers must have feelings too. They might like nice music. And in terms of nice music, have you ever wondered what Fibonacci sounds like? It's amazing how Fibonacci actually sounds quite musical, but then that's because music is based on maths and numbers, and Fibonacci is, of course, a mathematical sequence. So I think this is kind of quite nice. I can imagine the newest pop song to be kind of called Fibonacci and just be all of the songs. You know, you can imagine Katy Perry singing along to this. That's cool. Right. What else have we got? Right, so we've got Ruby to talk to our instruments, and we've got, we've also got Psych Pie, which is a digital synthesizer, and we've used Ruby to control that. But wouldn't it be cool if we could use Psych Pie to control our analog synthesizers as opposed to the built-in digital synthesizer? So it turns out that we can do that. So this is a song by a band, I forgot, Depeche Mode, I believe. Sorry, the song's called Blue Monday, and this was coded by Sam Aaron. This is how it sounds in Psych Pie. You may recognize this song. So that sounds pretty cool, but wouldn't it be more fun if we could try and get my instruments to play it instead? So it's more or less the same thing, except that I'm calling, using DRB actually to call my code running in another process, which should hopefully talk to my instruments. So if I just find that code and show you, oh, that's me, hello. DRB, here it is, right. So all I do is I have two instruments, and then we just play that note and start a DRB service. Let's go there. Oh no. Right. Oh, CD demos. Example. Right. So let's start up our server. DRB. Okay, so that's running in the background, and then if we go to Sonic Pi, hopefully, we should get some. We're getting instruments there, but we're not getting instruments over here. This one's not plugged in, that is why. Okay, and then I believe I might just need to edit the code, make that 2. Start that again. There we go. Here it was. So this is that same piece of music, but it's using Sonic Pi to generate, so we're writing Ruby code in Sonic Pi, but instead of sending it to the synthesizer inside my MacBook, we're sending it to these two Korg synthesizers here. So now I can come over here and start playing around with buttons. We can get a bit of a rave going on, I think, as well. And then we can stop it again. So that was Ruby in Sonic Pi talking to MIDI instruments via DRB. You know, every service we can think of. I think that was kind of cool. But the cool thing is, in the newest versions of Sonic Pi in the next few months, Sam is actually going to add in support for MIDI instruments natively, so we won't have to use this little hack. While we're talking about Sonic Pi, you should definitely go out and check their website, because it's got an amazing group of contributors, and of course it's open source. And one of the contributors, Xavier, he wrote this song, which I think you might quite, well, he didn't write the original, he transcribed a song into Ruby. So here is all of the Ruby, lots of it, and it sounds a bit like this. No, it won't, because we're not plugged in. Too many cables. Right, sounds like this. So this is all written in Ruby. And if you can hear that kind of drum beat, that is the noise function. That sort of sound. See, so instead of it sounding like noise like this, it sounds like an 8-bit computer from the olden days. So that kind of shows you what you can do with Sonic Pi, which is really, really cool. So we've controlled, let's see, we've controlled musical instruments with Ruby. We've then written Ruby in Sonic Pi. We've then used Sonic Pi to control our instruments. And then I was thinking, could I control Sonic Pi with my instruments? And so I went out and bought myself this little device, which is called a touchpad. It's a MIDI device that sends MIDI notes. So hopefully, Sonic Pi. I named it really usefully. Aha, MIDI to Sonic Pi. So hopefully, we should be able to control Sonic Pi using our MIDI touchpad. Where are we? Right. Ruby, MIDI synth. No, no, no. Oh, no. Need the gem. Will that work? Who knows? Yes! Oh, thank you. Let's hope the demo works. So in the code, basically, every time I press the button, it sends music to Sonic Pi. And the computer's plugged in. Let's see. It worked. So every time I'm pressing this, we're now sending Sonic Pi new notes to play. So now you don't even have to code Ruby anymore. You can just play instruments, as long as you write a little bit of code that sends the various data to Sonic Pi. So how cool is that? Imagine being able to program like this just by pressing buttons on a keyboard. Sonic. And so then I thought this was cool, using a little MIDI touchpad like that. And I thought, well, I've also now got a small size keyboard. I wonder if I can use my keyboard to send music to Sonic Pi. And so the same again. Instead of doing MIDI output from the computer to the instrument, you can also go the other way, input. So if I plug this in, that's the right one. So we're basically, every time the keyboard sends a note, we're sending that to Sonic Pi, and Sonic Pi should hopefully play it. And we want to select this one, I believe. Let's try this. Oops, turn that off. Let's try it again. There we go. So every time I now press my keyboard, I'm sending that MIDI string at very, very bottom there to Sonic Pi. So now I don't have to write any code. I can just play my very expensive analog synthesizer through a very less expensive digital synthesizer. With a delay, of course, because I don't know. My code is very bad. But now I can just do this all day, and I probably would. So that was analog instruments going towards Sonic Pi. Right. Unfortunately, my brainwave scanner seemed to break on the way here, but I was hoping to be able to show you what music I like by taking my brainwaves and using that to generate music. So if I can get this working again before the end of the day, you can all hear what kind of music I like by me generating it. So apart from that, that's not bad, just only one demo is broken. Right, and with that, we've made it. We're at the end. So thank you very much. Domo arigato.